Good morning. My name is Varsha from BSc First Year Chemistry Honors. Our chapter is Stereochemistry of Organic Compounds. Introduction. The molecular structure of compounds plays a very important role in the study of organic chemistry. During this study, one comes across many instances where a given molecular formula represents two or more compounds having different properties. This is evidently due to some difference in the molecular structure of these compounds. Such compounds which have the same molecular formula but different properties are known as isomers, and the phenomena is called isomerism. Isomerism. The concept of isomerism is an important feature of the study of organic compounds. It relates to the existence of different compounds which have the same molecular formula but different properties. Such compounds are called isomers. Iso means same, mers means parts. The difference in the property of isomers is due to the difference in the relative arrangement of atoms in their molecules. There are two types of isomerism: structural isomerism and space or stereoisomerism. Structural isomerism. This is the type of isomerism which is due to the difference in the arrangement of atoms within the molecule having the same molecular formula. The students is already familiar with the various types of structural isomerism. However, we shall present here a brief review for the sake of recapitulation. First is change or nuclear isomerism. This is a kind of isomerism which arises when the compounds having the same molecular formula differ only in the arrangement of carbon atoms in a chain. Thus, normal butane and isobutane having the same molecular formula C4H10 represents two chain isomers N-butane and isobutane. Similarly, there are three chain isomers having the molecular formula C5H12. First is N-pentane, second is isopentane, third is neopentane. Second is position isomerism. If two or more compounds with the same molecular formula have different position occupied by a characteristic atom or a group attached to carbon, position isomerism is said to exist. N-propyl chloride and isopropyl chloride afford an outstanding example of this type of isomerism. But these compounds have the same molecular formula C3H7Cl, the same carbon skeleton but different from each other in the position of attachment of chlorine atom. N-propyl chloride and isopropyl chloride. Similarly, there are two butenes C4H8 which differ in the position of double bond in the molecule, but1-ene and but2-ene. Third is functional isomerism. This type of isomerism is due to the presence of different functional groups in compounds having the same molecular formula. For instance, C2H6O represents two compounds. First is ethyl alcohol, second is dimethyl ether. These two compounds have internally different physical and chemical properties because of the presence of different characteristics groups. Acetone and propanaldehyde C3H6O represent another pair of compounds exhibiting functional isomerism. First is acetone, second is propanaldehyde. Fourth is metamerism. This type of isomerism is due to the difference in the distribution of a carbon atom on the either side of functional group in a compounds having the same molecular formula. For instance, diethyl ether and methyl chloropyl ether represent a pair of metamers having the molecular formula C4H10O. Diethyl ether and methyl propyl ether. Diethyl ketone and methyl propyl ketone having the molecular formula C5H10O furnish another case of metamers. First is diethyl ketone, second is methyl propyl ketone. Ring chain isomerism. This is a type of isomerism in which two compounds having the same molecular formula have open chain and ring structure respectively. For example, propene and cyclopropane having the molecular formula C3H6 afford a simple example of ring chain isomerism. Structure of propene and structure of cyclopropane. Similarly, but1-ene and cyclobutene are also ring chain isomers for each other. First structure is but1-ine and second structure is cyclobutene. Tautomerism. This is a special type of functional isomerism where the isomers exist simultaneously in a dynamic equilibrium with each other. The isomers which are involved in equilibrium are called tautomers. The structure of tautomers generally differ from each other in the point of attachment of one of the atoms in the molecule. In ketanol tautomerism, which is the most important type of tautomerism, the tautomers differ from each other in the point of attachment of a hydrogen. Thus, acetyl acetone exists as a tautomerism mixture of two forms, the ketoform and the enol form, which differ in the point of attachment of a hydrogen as shown below. First is when ketoform of acetyl acetone reacts, enolic form of acetyl acetone is formed. Similarly, ethyl acetoacetate exists as a mixture of keto and enoloic forms. When ketoform reacts, enoloic form is formed. Stereomerism. This is the type of isomerism which arises due to the difference in the arrangement of atoms in space. Its study is known as stereochemistry. In this unit, we shall discuss the important aspects of stereomerism. Stereoisomerism. The isomerism compounds which differ from each other only in the relative arrangement of atoms in space but resemble one another with respect to which atoms are linked to which other atoms are called stereoisomers, and the phenomena is known as stereoisomerism. There are three types of stereoisomerism. First is optical isomerism, second is geometrical isomerism, third is conformational isomerism. Before proceeding further, it may be pointed out that the different structure of conformational isomers of a substance are non-superimposable of one another but are easily interconverted into each other by rotation around single bonds. In contrast to this, the different structure of optical or geometrical isomers and non-superimposable know one another and at the same time they cannot be interconverted except by breaking and making the bonds. For this reason, optical and geometrical isomers are also collectively known as configurational isomers, while conformational isomers of a substance exist only as a mixture of different forms. The configurational isomers can be prepared as distinct individual substances. We shall now discuss the different types of stereoisomerism, starting with optical isomerism. Optical isomerism. This is a type of stereoisomerism in which the isomeric compounds resemble one another in their chemical reactions and most of the physical properties, but differ in their effect and polarized light. We shall now first review some fundamental terms concerning optical isomerism and then discuss other features of optical isomerism. Tetrahedral concept of carbon. It is well known that in methane and all other compounds having carbon bonding to four other atoms or a group by single bonds, the four bonds of carbon are directed towards the four corners of tetrahedron. The tetrahedral concept of carbon, put forward by Lee Bell and Wandsworth, is very helpful in understanding the phenomena of optical isomers. A representation of the tetrahedral carbon atom is shown in figure 2.1 by molecular model and in figure 2.1b by Wade's formulae. The figure 2.1 representation of tetrahedral carbon. Figure 1 represents the molecular model and figure B represents the Wade's projection. It should be noted that by convention the Wade's represents the bonds pointing towards the observer out of the plane of the paper. The Hertz line or dashed line represents the bond behind the plane of the paper. The normal lines show the bonds in the plane of the paper. Polarized light. An ordinary ray of light consists of electromagnetic waves of various wavelengths and its vibrations takes place in all planes at right angles to the direction in which it travels. A ray of light which consists of waves having only one wavelength is known as monochromatic light. Even such a ray has its vibration in all planes. However, if a ray of monochromatic light, such a yellow light from a sodium flame, is passed through a nickel prism, a special prism made for calcite, which is a particular crystalline form of calcium carbonate. The wave motion of emergent light is restricted to only one plane. Light whose vibration takes place in one plane is known as plane polarized light or just polarized light. The plane along which vibration takes place is known as plane of polarization, and the nickel prism used for polarizing the light is known as polarizer. Figure 2.2 represents the vibration in ordinary and polarized forms of light. Optical activity. There are certain substances which can rotate the plane of polarized light. For instance, when polarized light vibrating in a certain plane is passed through cane sugar solution, the light which emerges out vibrates in a different plane. Such substances which can rotate the plane of polarized light are said to be optically active, and the property is called optical activity. The substances which rotate the plane of polarized light towards the right are termed as dextrorotatory, while those who rotate towards the left are called levorotatory. The instrument used for measuring the angle of rotation of the plane of polarized light is known as polarimeter. The angle of rotation through which plane of polarized light is rotated by an optically active substance depends upon many factors, which are: first is nature of the compound, second is length of the liquid column through which the light passes, third is concentration of the solution and the nature of the solvent, fourth is temperature, fifth is wavelength of light used. Specific rotation. In order to compare the rotatory powers of different substances, optical activity is expressed as specific rotation. It is the angle of rotation of plane of polarized light produced by a tube 1 decimeter in length filled with a solution having 1 gram of substance per ml of solution at a temperature T using light of wavelength 5893 angstrom from sodium vapor lamp. This light is called D line of sodium. Specific rotation is generally calculated from this equation: observed angle of rotation divided by L into D, where D represents the weight in grams of solute in 1 ml of solution or density of the substance if it is liquid, and L is length in decimeters of a tube filled with sample. For instance, the specific rotation of cane sugar solution at 293 Kelvin is plus 66.0 degree, limit D to 93. Elements of symmetry. The phenomena of optical activity is essentially related to lack of symmetry in a molecular structure. A simple method to decide whether a molecule is symmetrical or not involves there a criteria of symmetry known as elements of. An element of symmetry may be defined as a plane, light, or a point with respect to which the structure possesses a definite symmetry. There are three elements of symmetry as discussed below. First, plane of symmetry. It is an imaginary plane passing through an object or a structure which divides the object or structure into two halves, such that one half is mirror image of the other. For example, a beaker has a plane of symmetry as shown in figure 2.3a. Similarly, the molecule of propanoic acid has a plane of symmetry as shown in figure 2.3b. In a study of optical isomerism, the plane of symmetry may be shown simply with the help of three-dimensional formula, or more conventionally by using planar formula as shown in figure 2.4a and 2.4b for the molecule of 2,2-dibromobutane, Human end is the perfect example of an object having no plane of symmetry. 2-chlorobutane, lactic acid, and alanine are some examples of molecules which do not have any plane of symmetry. Structures of 2-chlorobutane, lactic acid, and alanine. Second is center of symmetry. It is an imaginary point within a molecule at which all the straight lines joining identical points in the molecule cross each other. For example, the center of symmetry in a molecule of 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid is shown below in figure 2.2. It may be noted that a structure can have more than one plane of symmetry, but no structure can have more than one center of symmetry. Third is axis of symmetry. It is an imaginary line passing through the molecule so that when the molecule is rotated about this line, exactly similar geometrical arrangement appears more than once in one complete revolution. If the identical arrangement appears twice in one complete revolution, the axis is called twofold axis of symmetry, denoted as C2 axis. If the similar arrangement appears thrice, it is threefold axis of symmetry, and so on. For example, trans 1,2 dibromocyclo propane possesses a C2 axis of symmetry in the plane of the ring, which bisects the bond between carbon atoms 1 and 2 and intersects the carbon atoms 3 as shown in figure 2.6. When rotated around the axis, the same arrangement appears after every 180 degree. Alternating axes of symmetry or rotation reflection axis. This is another element of symmetry which is rarely used. A molecule is said to have an n-fold alternating axis of symmetry if rotation by an angle of 360 by n about the axis followed by reflection in a plane perpendicular to that axis gives a molecule which cannot be distinguished from the original molecule. For example, 1,3-diethyl 2,4 dimethyl cyclobutane possesses a two-fold axis of symmetry as shown below. If the molecular A is rotated by an angle of 180 degree about the axis S2 which possesses through the center of the ring, it gives a molecular B. The reflection of B in a plane perpendicular to the axis gives the original molecule A. It may be noted a one-fold alternating axis of symmetry corresponds to a plane of symmetry while a two-fold alternating axis of symmetry correspond to center of symmetry. Molecular chirality, chiral and achiral structures. Chiral structures. A structure or object is said to be chiral if it is not superimposable on its mirror image. Such a structure does not have either a plane or center of symmetry. The most perfect example of a chiral object is human hand. It does not have any plane of symmetry and cannot be superimposed on its mirror image. If you hold your left hand up to a mirror, the image looks like a right hand, but if you try to superimpose one hand over the other, you cannot do it in figure 2.7. Similarly, a right-handed glove and a left-handed glove are chiral objects. A very large number of organic molecules such as 2-chlorobutane and lactic acid are known to have chiral structure as they are not superimposable on their mirror images. There are some mirror images of non-superimposable mirror images. The substances having chiral structure are said to be possess the property of chirality. It should be noted that chirality is the property of complete object or structure and not of its parts. It may also be noted that even though There are three kinds of elements of symmetry. Chirality is primarily related to lack of plane of symmetry and the center of symmetry. Achiral structures. A structure or object which has a plane of symmetry and is superimposable on its mirror image is known as chiral. Such a structure always possesses a plane of symmetry or a center of symmetry. For example, the letter A and the button on your shirt represents a chiral structure or objects. It can be easily seen that each of these has a plane of symmetry and is superimposable on its mirror image. In figure 2.8, a chiral structure are shown. Methane and carbon tetrachloride are perfect example of molecules having chiral structure as they are superimposable on their respective mirror image. There are some superimposable mirror images of methane and 2-chloropropane. Third is origin of chirality in organic compounds. Most of organic compounds which are chiral in nature owe their chirality to the presence of a carbon atom bonded to four different groups. Such a carbon is termed as chiral carbon or chiral center or stereogenic center or stereocenter, earlier known as asymmetric carbon. A stereogenic center or chiral carbon is a carbon atom which is bonded to four monovalent atoms or groups such as C. There can be two different tetrahedral models for C which differ in spectral arrangements of various groups attached to carbon as shown in figure 2.9. Figure 2.9 represents non-superimposable mirror image model of C. Each of the two models is related to other like an object to its mirror image and one cannot be superimposed on other. No matter how we turn or twist them, each of these models therefore represents a chiral structure. Similarly, we can have two non-superimposable mirror images structure for any compound which contains a stereogenic center for chiral center. For example, lactic acid 2-methyl 1-butanol are chiral molecules since each of them contains a chiral center. In figure 2.10, there are some non-superimposable mirror image models of lactic acid and 2-methyl butanol. It must be emphasized, however, that certain molecules may contain more than one stereogenic or chiral center and still they may be achiral or non-disymmetric. For instance, 2,3-dichlorobutane which has two chiral centers, exist in many isomeric forms, one of which is not chiral because it has a plane of symmetry as shown below. Chiral molecules not containing any chiral carbon. There are certain molecules known to exist which are chiral even though they do not contain any chiral carbon. For example, allenes represent a well-known class of such compounds as illustrated below. Non-superimposable mirror images of 2,3-pentadiene. It may be seen by molecular models by chirality in 2,3-pentadiene arises due to the fact that the two groups singly bond to one of the end of carbon atoms of allene system are in a different plane than the two groups singly bond to other end carbon of the allene system, substituted by phenyls, constitute another example of such compounds which are chiral without containing any chiral carbon atom. The chirality in such compounds arises due to the fact that the two benzene rings lie in different planes perpendicular to each other. Non-superimposable image of 6,6-dinitrofenic acid. Optical isomerism, enantiomerism, It has been observed that optically active substances always exist in two or more isomeric forms which differ with respect to their optical activity or their action on plane polarized light. As already stated, the isomers which resemble one another in their chemical reaction and most of the physical properties but differ in their effect on polarized light are called optical isomers, and the phenomena is known as optical isomerism. There are two main types of optical isomerism. These are enantiomerism, diastereomerism. We shall now discuss these two types starting with enantiomerism. Enantiomerism. It is the simplest kind of optical isomerism which was discovered by Pasteur in 1848 as a result of his work on the salts of tartaric acid. He observed that optically inactive sodium ammonium titrate consists of a mixture of two distinct types of crystals. These two types of crystal were not superimposable on each other, although their shapes were like mirror images of each other. The relationship between the two types of crystal may be compared to that between a pair of right and left handed gloves. Pasteur separated the two types of crystal from the original sample with the help of a magnifying lens and a pair of tweezers. Unlike the original optically inactive sample, each type of crystal was found to be optically active in its aqueous solution. Moreover, the specific rotation of the solution of one type of crystals was found to be equal but of opposite sign to that of the solution of second type of crystals. Considering the fact that difference in optical rotation was observed in a solution where the solute exists in the form of simple molecules, Pasteur proposed that the molecules constituting the two types of crystals were also non-superimposable mirror images of each other. Such isomers whose molecular structure are not superimposable mirror images of each other and which rotate the plane polarized light equally but in opposite direction are known as enantiomers or enantiomorphs. The phenomena of mirror image is isomerism is called enantioisomerism. Since the mirror image of isomers differ only in the spatial arrangement of atoms, enantiomerism represents a type of stereoisomerism. Explanation of enantiomerism. The existence of mirror image isomers or enantiomers was justified by Wandt's on the basis of tetrahedral concept of carbon atom. Let us try to apply this concept to an imaginary compound of the type CABCD in which a carbon atom is attached to four different groups. Such a compound can be represented by two different tetrahedral models which differ in the spatial arrangements of various groups attached to the carbon atom. The two models are related to each other like an object and its mirror image, and one cannot be superimposed over the other, no matter how we turn or twist them. These models represent two enantiomers of the compound. For example, let us draw tetrahedral formula of enantiomeric forms of substances such as lactic acid and 2-methyl-1-butanol, which are known to exhibit enantiomerism. In such of these cases, we find that it is possible to construct two formula which are non-superimposable mirror images of each other and such they represent the different enantiomers. It may be pointed out, however, that if the compound containing tetrahedral carbon atom does not have four different groups attached to the carbon, then the molecules are superimposable on their mirror images. This is illustrated below with the help of bromochloromethane CH2ClBr Such compounds do not exhibit enantiomerism because all their molecules are of the same type. Figure 2.11 represents no enantiomerism possible as mirror images of bromochloromethane are superimposable. Fundamental condition for enantiomerism. It has been shown that enantiomer molecules are always non-superimposable mirrors images of each others. The known the known superimpossibility of mirror images invariably arises due to chiral nature of the molecules as already stated. A molecule is termed as chiral if it has no plane or center of symmetry and is therefore non-superimposable on its mirror image. Chirality in most of the enantiomeric molecules is itself due to the presence of at least one chiral carbon in the molecule. For example, lactic acid and 2-methyl 1-butanol contain one chiral carbon each and therefore exist as enantiomeric forms. At the same time, there can be molecules on such as 2,3-pentadiene and substituted diphenyls such as 6,6-dinitrophenic acid which do not contain any chiral carbon but they will still possess the property of chirality and thus exhibit enantiomerism. It may be concluded, therefore, that chirality, the property of existing as non-superimposable mirror images, is the fundamental and only condition of enantiomerism. Characteristics of enantiomers. The important characteristics of the enantiomerism of a given substance are described below. They have identical physical properties such as melting point, boiling point, densities, solubilities, refractive indices. The only difference lies in the direction of rotation of plane polarized light, although even here the magnitude of specific rotation is the same. For example, the specific rotation of the two enantiomeric 2-methyl 1-butanols are plus 5.76 degree and minus 5.76 degree respectively. Second is they have identical chemical properties except in reaction with other optically active compounds. For example, the ordinary chemical reaction of lactic acid are exactly like those of lactic acid. Moreover, there is no difference in the speed of such reactions. There may be difference, however, in the rates of reactions at which the two enantiomers reacts with some other optically active compounds. For instance, the rate of esterification of plus lactic acid with plus sec butyl alcohol, which is optically active, should be different from the rate of esterification of minus lactic acid with the same alcohol. Third is they have different biological properties. In contrast to physical and usual chemical properties, enantiomers are quite different in their biological properties. For example, plus sugar plays an important role in animal metabolism, whereas minus sugar is not metabolized at all. Similarly, plus tartaric acid is readily consumed by the mold Penicillium glaucium, while minus tartaric acid is not. Fourth is when equal quantities of enantiomers are mixed together, it results in the formation of an optically inactive form called racemic modification or racemic mixture of a or racemate. The racemic modification is distinguished by using the prefix before the name of the compound. For example, if equal quantity of lactic acid and lactic acid are mixed with each other, we got racemic or lactic acid which is optically inactive. Enantiomerism and optically activity. We have just learned that fundamental condition for the phenomena of enantiomerism is the chiral nature of the molecules and the fundamental difference between enantiomers of a given substance is the direction of optical rotation. Let us now examine as to what structural features give rise to optical activity and how is it related to the phenomena of enantiomerism. A single individual molecule of nearly every substance can cause some rotation of the plane polarized light. When a beam of such light passes through the molecule, the direction and extent of rotation caused by a particular molecule depends upon the orientation in the beam of light. But in actual practice, it is not possible to have with us only a single molecule of any substance, even a very small sample of substance being made up of very large number of molecules distributed at random. Therefore, what happens in most of the cases is that for every molecule that rotates the plane of polarized light, there is another identical molecule oriented as the mirror image of the first, which exactly cancel its effect. As such, no optical rotation can be observed. This means optically inactivity of a substance is basically due to the random distribution of identical molecules which can serve as mirror images of each other. But in case of chiral molecules, the mirror image of any one molecule is not another identical molecule. Rather, it is a different isomeric molecule. Now, if we take a pure sample consisting of a single enantiomer, no molecule can serve as the mirror image of another. As a result, there cannot be exact cancellation of rotation, and as such optical activity is observed. Thus, a given sample of a substance can exhibit optical activity only if the constituent molecules are non-superimposable mirror images of one another. In other words, chirality is also the fundamental and sufficient condition for optically activity. Representation of stereoisomers. Flying weight formula. If we have so far used the molecular models and three-dimensional tetrahedral formula to represent the stereoisomers, the tetrahedral formula can also be drawn in a somewhat different but more convenient way as flying weights formula. For drawing these formula, the molecule is oriented in a space in such a way that the two bonds to the stereo center point towards the observer while the other two bonds are directed away from the observer. The bonds pointing towards the observer are represented by wedges drawn horizontally. The bonds pointing away from the observer are represented by dotted lines drawn vertically. For example, the molecular model of tetrahedral formula and flying wedge formula of one of the enantiomers of lactic acid may be shown as follows. Molecular model, tetrahedral formula, flying wedge formula. Similarly, three kinds of representation of other enantiomers of lactic acid can shown in this. The tetrahedral and flying wedge formula of enantiomers of 2-butanol are given below. Planar representation of three-dimensional formula, Fisher projection formula. The use of molecular models is no doubt the most suitable method of showing the spectral orientation of atoms constituting the molecules, but it is not very convenient to represent the formula of compounds on paper. Therefore, a simple although not foolproof method was introduced by Emil Fischer for projecting their dimensional formula of chiral molecules on planar surface. The planar representation are called Fischer projection formula. Procedure for writing Fischer projections. For writing the projection formula, the following procedure is adopted. First is the chiral molecule is viewed in such a way that two groups bound to chiral carbon towards the observer while the other two groups point away from the observer. Second is the various groups attached to the chiral carbon are then projected to the plane of the paper in the form of a cross so that horizontal lines represents bond pointing towards the observer while vertical lines represents bond pointing away from the observer. Third is the vertical part of the projection formula should represent as far as possible the longest chain of carbon atoms in the molecule, with the carbon atom to be numbered as 1 according to IUPAC system being written at the top. The chiral carbon atom is not written at all. While writing the projection formula, it is taken for granted that the chiral carbon is located where the horizontal and vertical lines cross each other. For instance, the projection formula of the two enantiomers of lactic acid may be represented as shown ahead. Molecular models and Fisher projection formula of two enantiomers of lactic acid. It should be noted that more than one Fisher projection can be written for the same compound depending upon which bonds are shown horizontally and which bonds are drawn vertically. It is therefore necessary to test whether the given Fisher projection represents the same stereoisomer of a compound or not. This can be done by using the following rules. First is a Fisher projection may be imagined to be rotated from end to end without lifting it from the plane of the paper. Rotation by 180 degree in the plane of the paper does not bring about any change in the configuration. For example, if the projection face of lactic acid is rotated through 180 degree in the plane of the paper, it gives projection second since no change in configuration takes place in rotation by 180 degree. Projection first and second represent the same stereoisomer of lactic acid, but rotation by 90 degree or 270 degree leads to inversion of configuration, so that the new configuration represents the enantiomer of original compounds. Second is if two position of two groups or atoms about the chiral carbon are interchanged, it also leads to inversion of configuration. But if we carry out two such interchanges, the configuration remains unaltered. It is quite evident from the above that one interchange is equivalent to rotation by 90 degree or 270 degree, while two interchanges are equivalent to rotation by 180 degree. Chiral and achiral molecules with two stereogenic centers diastereomerism. We have learned that compounds containing one stereogenic center exist in two stereoisomeric forms, which are known as enantiomers of each other. What about compounds containing two stereogenic centers? Quite exactly, such compound can exist in more than two stereoisomeric forms. To illustrate this statement, let us consider the case of 2,3-dichloropentane, which contains two stereogenic centers. Since the four different groups attached to one stereogenic center are not the same as those attached to the other, the two chiral carbon atoms are dissimilar from the another. There are so many as four stereoisomers as possible. This compound examination of formula first and second reveals that they are no impossible mirror images of each other and hence represent a pair of enantiomers. Similarly, third and fourth are also non-superimposable mirror images of each other and thus represent another pair of enantiomers. It becomes immediately clear that the two formula have identical configuration about one chiral but mirror image configuration about the other chiral carbon. The net result is that the two forms are neither identical nor mirror images for each other. Such stereoisomers of a substance which are not mirror images of each other are known as diastereomers. In addition to formula first and three, formula first and fourth, second and third, second and fourth also represent pairs of diastereomers. Fisher projection formula and flying wedge representation of four stereomerisms of 2,3-dichloropentane are given below. flying wedge representations. 3-chlorobutanol affords another example of a compound having two dissimilar chiral carbon atoms which can exist in four stereoisomeric forms as given below. It may be seen that structure 5 and 7th and 8th and 6th and 7th, 6th and 8th represent pairs of diastereomers. Characteristics of diastereomers. The important characteristics of diastereomers are as follows. They show similar but non-identical chemical properties. In the reaction of two diastereomers with a given reagent, the rates of reaction are generally different from each other. This is because diastereomers have different energies of activation for a particular reaction and therefore they react at different rates. Second is they have different physical properties such as melting points, boiling points, densities, solubilities, and refractive indices. Third is their specific rotation are also different from each other. In fact, some of the diastereomers may be even optically inactive. It should be noted that geometrical isomers are also diastereomers of each other but they are optically inactive. On account of different physical properties, diastereomers can be rather easily separated from each other by physical methods such as fractional crystallization, fractional distillation, chromatography, etc. Comparison of diastereomers and enantiomers. First is diastereomers. These are stereoisomers which do not have a mirror image relationship, but in enantiomers they have a mirror image relationship. Second is they have different physical properties such as melting point, boiling point, solubility in a given solvent and density. But in enantiomers they have identical physical properties such as melting point, boiling point, solubility in a given solvent and density. In diastereomers, these can be separated by fractional distillation, fractional crystallization, and adsorption chromatography. In enantiomers, they cannot be separated by such methods. In diastereomers, these may have optical rotation in the same or opposite direction but to a different extent. But in enantiomers, these have optical rotation in opposite direction but to the same extent. In diastereomers, these have identical chemical properties but differs in the rate of reactions with optically active compounds. But in enantiomers, these have identical chemical properties except with other optically active compounds. Erythro and threoisomers. A special system of nomenclature is sometimes used for distinguish between diastereomers in which two of atoms or group attached to one stereogenic center are the same as the two atoms or groups attached to other stereogenic center. This method is derived from the names of two diastereomeric carbohydrates, erythrose and threorose as shown below. Structure of erythrose and threorose. If the two similar groups are on the same side in a Fisher projection formula of a molecule, the diastereomer is known as erythroisomer. If the two similar groups are on the opposite sides in the projection formula of a molecule, the diastereomer is known as threoisomer. For example, of the four isomers of 3-chloro-2-butanol, one pair of enantiomers is known as erythro, while the other enantiomer is known as threo as illustrated below. It may be seen that any compound of one pair of diastereomer of any compound of other pair. Mesocompounds. Let us consider a compound containing two similar chiral centers having the same set of four different groups attached to each of the chiral carbon atom. A typical example of such compound is provided by tartaric acid. In view the fact that it has two chiral centers, one may accept the existence of four stereomers of the acid having the configuration IX, XI and XII. Formula IX and X are non-superimposable mirror images of each other and they represent a pair of optically active enantiomers. Formulae Xi and XII again have a mirror image relationship. Close examination of these formulae, however, shown that no one of these structure may be superimposed on the other just by rotating it through 180 degree within the plane of the paper. These two formulae therefore represent two superimposable mirror image molecules of the same compound. Further examination of formula Xi reveals that in spite of two chiral centers in it, the molecule is achiral. This is because it has a plane or symmetry, one half of its molecule being mirror image of the other half. As such, the compound represented by formula Xi is optically inactive. Such an optically inactive compound whose molecules are not chiral, even though they contain two chiral centers, is known as meso compound. As explained above, the molecules of such compounds are superimposable on the mirror images. Thus, tartaric acid exists in three forms: negative tartaric acid, positive tartaric acid, formula IX and X, and mesotartaric acid, formula XI or XII. Although optically inactive and mesotartaric acid represent a diastereomer of negative or positive tartaric acid, Fischer projection formulae and flying wedge formulae of three isomers of tartaric acids. Fischer projection formula and flying wedge representation. It should be noted that meso compounds are permanently inactive and are said to be internally compensated. This is because one half of the molecule cancels the rotation due to the other half. 2,3-dichlorobutane affords another example of a compound which contains two chiral carbons and exists in the three forms: two optically active forms and one mesomization. The conversion of an optically active compound into a racemic mixture containing equal amounts of the original compound and its enantiomer is known as racemization. Racemization can be brought about by one of the following methods depending upon the nature of the compound. First is by action of heat. Quite often an optically active enantiomer changes into a racemic mixture by the action of heat. For example, when plus tartaric acid is strongly heated with water, it gets converted into a mixture of racemic and mesotartaric acid. Second is by the action of chemical reagents. Racemization is also brought about the presence of foreign substances in the solution of an optically active substances. For example, addition of sodium hydroxide of plus or minus lactic acid leads to the formation of racemic mixture. Third is autoracemization. In some cases, racemization takes place by merely keeping the substance at room temperature for some time. This is known as autoracemization. For example, any one of the enantiomers of dimethyl bromosuccint changes into a racemic mixture of standing at room temperature. Mechanism of racemization. Different mechanisms have been developed for the racemization of different types of compounds, but in majority of cases, racemization is believed to take place through the formation of some intermediate which is no longer chiral in nature as explained ahead. acid catalyst racemization of an optically active aldehyde or ketone in which the chiral carbon carries a hydrogen and region alpha position with respect to a carbonyl groups takes place through enolization, i.e. the intermediate formation of an achiral enol by tautomerism change, the enolic form being unstable, reverts to the chiral keto form, but in doing so it produces plus and minus enantiomers in equal quantities and thus racemization takes place. This shown ahead with the help of 3-methyl 2-pentanone. Irrespective of whether the starting compounds is plus or minus the methyl 2-pentanone, the final product is a racemic mixture since both the enantiomers are formed in equal quantities. Base catalyst racemization of minus lactic acid takes place through the formation of an achiral carbanion as shown below. The final product would be racemic mixture whether we start with minus or plus enantiomer of lactic acid. We shall come across many examples of chemical reaction in the text such as SN1 reaction of alkyl halide discussed in chapter 9 which are accompanied by complete or partial racemization. Partial racemization means that one enantiomer may be formed in larger amount than the other so that the mixture of two will not be completely inactive. Internal and external compensation. Internal compensation. It has been stated above the meso compounds are actively inactive because their molecules are not chiral. Even though they contain two chiral centers, for example, it is clear from the structural formula of mesotartaric acid that the top half of the structure is the mirror image of the bottom half. As such, the optically active due to the one chiral center is counterbalanced by optically activity due to other and the compound is optically inactive. The counterbalancing of optical activity of one half of a molecule by other half of is known as internal compensation and the molecule is said to be internally compensated. An internally compensated molecule is permanently inactive. External compensation. In a equimolar mixture of two enantiomers, say plus and minus lactic acids, the molecules of one enantiomer are present in a quantity equal to those of the other enantiomer. This means that for every possible orientation of one enantiomer, which can cause rotation in a particular direction, say towards right, a molecule of the other enantiomer would be in a mirror image orientation. Therefore, exact cancellation of all rotation would take place and the equimolar mixture would be optically inactive. The cancellation of rotation of an enantiomer by the other in an equimolar mixture of two enantiomers is known as external compensation and the racemic mixture is said to be externally compensated. It may be pointed out that if the two enantiomers are not mixed in equimolar quantities, the rotation caused by one enantiomer is not exactly cancelled by other. As such, the mixture is still exhibits some optically inactive activity. The direction of rotation corresponds to that of the enantiomer present in large quantity, but the specific rotation is lesser. In this way, partial compensation takes place and the mixture formed is said to be partially racemized. Comparison of external and internal compensations. External compensation. First, this is due to the mirror image relationship between the structures of the molecule of two enantiomer mixed together. In internal compensation, this is due to the mirror image relationship between the structure of two halves of the same molecule. Second is in this type of compensation, the molecules of one enantiomer cancel the rotation of the other enantiomer. Second is in this type of compensation, one half of the molecule counterbalance the rotation of other half. Third is the racemate formed is a mixture of two isomeric compounds. In internal compensation, meso or internally compensated compounds represent a single pure compound. Fourth is it is possible to have complete or partial external compensation of rotation so as to cause complete or partial racemization. In internal compensation, partial internal compensation is not possible. In external compensation, it is a reversible process and the racemic mixture can be resolved into plus and minus enantiomers. But in internal compensation, it is permanent effect and it is not possible to resolve an internally compensated molecule into optically active forms. Resolution of racemic mixture. The process of separating a racemic mixture into the enantiomers is called resolution. It is not easy to carry out resolution in actual practice. This is because enantiomers have identical physical and chemical properties, which makes their separation from each other very difficult. Therefore, special methods have been introduced for this purpose. Mechanical separation. If the enantiomers of a substance exist in a well-defined crystalline forms, the separation can be done by hand picking with the help of a magnifying lens and a pair of tweezers. For example, the enantiomers of sodium ammonium tartrate can be separated by this method. Limitations. First, the method has very limited applications as very few enantiomeric substances exist in the form of mechanically separable crystals. Second is the method is very laborious and time consuming. Biochemical separation. This method involves the use of microorganisms for bringing about resolution. If certain bacteria, yeasts, or molds are allowed to grow in a dilute solution of a racemic modification, one of the enantiomers is selectively consumed by the microorganism, while the other is left behind. For example, when the mold Penicillium glacium is allowed to grow in a solution of a racemic ammonium tartrate. The mold completely destroys plus ammonium tartrate while minus ammonium tartrate is left practically unaffected. A limitation of biochemical separation. The main disadvantage of this method is that one half of the material is destroyed during separation, and second is as the separation is carried out only in dilute solution, the process is very slow and only small amount of material can be separated. Chemical separation. This is probably the best method of resolution. It involves the conversion of racemic mixture into the mixture of diastereomers of some other substance by reaction with an optically active reagent. Since diastereomers have different physical properties, the mixture of diastereomers can be easily separated through fractional crystallization, fractional distillation, chromatography, etc. Each of the diastereomers is then suitably treated to generate a pure enantiomer of the original substance. For example, if racemic mixture of plus and minus lactic acid is treated with a single enantiomer of an optically active base, say minus brucine, it would result in the formation of a mixture of two crystalline salts. The two salts formed would be minus brucine and plus lactate, and minus brucine and minus lactate, while brucine parts of these salts has the same configuration. In both cases, the acid parts have non-superimposable mirror image configuration in two cases, so that the two salts represent two diastereomers. As such, the crystals of two salts differ in their solubilities, can be separated by fractional crystallization. Once the separation has been achieved, reaction of each salt with hydrochloric acid would generate a free lactic acid in pure enantiomeric form. Apart from the separation of racemic acids or bases by this method, it can also be employed for the separation of racemic alcohols, aldehyde, etc. By treatment with suitable optically active reagents. Chromatography. These days, chromatography techniques such as adsorption chromatography using optically active adsorbents, paper chromatography, and gas chromatography also being used for resolution. In adsorption chromatography, the solution of racemic mixture in a suitable solvent is passed through a column packed with optically active adsorbent when differential adsorption for the enantiomers takes place. This is followed by elution with suitable solvents to get each enantiomer separately. Configuration and its specification. Configuration. The arrangement in a space of the atoms or groups constituting a stereoisomer is called its configuration. For example, the configuration of two enantiomers of lactic acid are first and two shown below. One of these configurations represents dextro or plus lactic acid, while the other represents levo or minus lactic acid. Specification of configuration D and L notations. When we state that one of the enantiomers of lactic acid has the configuration first while the other has configuration second, we merely represent the two possible configuration of the enantiomers of lactic acid. What is not indicated is which configuration represents which isomer. Which one of the two enantiomers plus or minus has the configuration I and which has the configuration second. In the other words, we don't know actual or absolute configuration of each of the two enantiomers. In the earlier days of the study of stereochemistry, it was not found possible to determine the absolute configuration of the compounds. Fortunately, it is not always necessary to know the absolute configuration of an optically active compound. On the other hand, we are more interested in knowing the relative configuration of different compounds. For example, when an optically active compound undergoes a chemical reaction, we are mainly interested in whether the configuration of reactant and its product are same or different and not in their actual configurations. Relative configurations standard reference compound. To assign relative configurations to various optically active compounds and to indicate their relationship, what was done was to choose a standard reference compound and fix its configuration arbitrarily as proposed by Emil Fischer in 1885. The compound chosen as the standard was glyceraldehyde and its two enantiomers were designed by the symbol D and L. It must be made clear that these symbols D and L refer to configuration and are quite different from the prefixes D and L, which refer to the direction of rotation. Plus glyceraldehyde was arbitrarily assigned by the configuration third, in which the OH group attached to chiral carbon atom is towards right and was given the symbol D. The negative enantiomer was assigned the configuration fourth, in which the OH group attached to chiral carbon is towards left and was given the symbol L. Three-dimensional and planar representation of two enantiomers of glyceraldehyde. Regions for selecting glyceraldehyde as the standard. Glyceraldehyde was chosen as the standard mainly because of the following reasons. First is it is simplest carbohydrate and aldehydride, and its configuration could be easily related to those of the other carbohydrates, which are stereochemically very important compounds. Since glyceraldehyde contains very reactive functional groups, it could be converted into many other types of compounds. In this way, it could be configurationally related to a large number of compounds. Correlation of configuration. Many other compounds were then assigned relative configuration by relative their configuration to that of D or L glyceraldehyde. For this purpose, either the compound under examination is converted into D or L glyceraldehyde or D or L glyceraldehyde is converted into the given compound by means of reaction which do not involve breaking of bonds to a chiral center. The general principle involved in correlating the configuration of two compounds is that if a reaction does not involve the breaking of a bond about a chiral center, the configuration about the stereogenic center remains unchanged. Some important examples of the correlation of the configuration are given below. First is when glyceric acid can be obtained by the oxidation of D plus glyceraldehyde as shown below. Since this reaction does not involve breaking of bonds about the stereogenic center, minus glyceric acid must have the same configuration as that of glyceraldehyde taken, i.e. D configuration. D plus glyceraldehyde reacts in the presence of oxygen. D minus glycerolic acid is formed. Second is the configuration of plus lactic acid was stabilized to be similar to that of L minus glyceraldehyde by the following reactions. None of the reaction involves breaking of the bond above the stereogenic center. Third is when D plus glyceraldehyde was converted into tartaric acid by the series of the reactions shown below, a mixture of two products was obtained. These two products differed from each other in their configuration around newly created stereogenic center. One of the products was the inactive or tartaric acid, the other was the optically active tartaric acid, which rotated the plane of light to the left. It was minus tartaric acid since it was obtained from D-glyceraldehyde by reaction which did not involve breaking of bonds around the original chiral center. It was assigned D configuration, i.e. the same as that of starting glyceraldehyde. Since D negative tartaric acid was assigned configuration Vi and L positive tartaric acid would naturally have the mirror image configuration VII. It must be emphasized that there is no direct relationship between absolute configuration and direction of rotation of polarized light. Two substances may have similar relative configuration and yet may have rotated the plane of light in the different direction. For example, D plus glyceraldehyde and D minus glyceric acid have similar configuration even though the former is dextrorotatory while the latter is levorotatory. Similarly, two compounds may have different configuration and even then they may rotate the plane of light in the same direction. For example, D plus glyceraldehyde and L plus lactic acid have opposite configuration but the same sign of rotation. There are some structures of D plus glyceraldehyde and L plus lactic acids absolute configuration. It was only in 1951 that by using X-ray diffraction studies Voigt was able to determine the absolute configuration of a compound, i.e. the actual reagent arrangement in a space of the atoms or groups constituting of a particular stereoisomer. The compound whose absolute configuration was determined absolute configuration. It was only in 1951 that by using X-ray diffraction studies, Voigt was able to determine the absolute configuration of a compound, i.e. the actual arrangement in a space of the atoms or group constituting a particular stereoisomer. The first compound whose absolute configuration was determined was sodium rubidium salt plus tartaric acid. By Voigt found that plus tartaric acid actually has the same configuration which it was previously assumed to have on the basis of configurational relationship between glyceraldehyde and tartaric acid. If the assumed configuration relations of plus tartaric acid was correct, the assumed configuration of two enantiomers of glyceraldehyde must also be correct. As such, the configuration of all the other compounds derived by correlation with glyceraldehydes must be correct ones. Thus, the relative configuration assigned to D minus glyceric acid, L minus lactic acid, carbohydrates, and large number of other compounds actually represent their absolute configuration. The absolute configuration of some simple but stereochemically important compounds are given below in the planar form. Limitations of D and L system of configuration. The system of designating the configuration as D and L is essentially based upon the configurational relationship to one or the other enantiomers of glyceraldehyde, but the procedure followed has certain limitations. It has been found that in some cases a given compound can be related by a sequence of reaction to a known compound having D configuration, but at the same of the known compound. This leads to an ambiguous situation where the same compound may be assigned either D or L configuration. It may, however, be pointed out that in the case of carbohydrates and amino acids, certain conventions have been adopted due to which the system of assigning D and L configuration is found very useful in these classes of compounds. Geometrical isomerism and its cause. Geometrical isomerism is a type of stereoisomerism which is exhibited by certain compounds containing double bonds and arises due to hindered rotation about the double bond. We will first discuss geometrical isomerism in compounds containing carbon-carbon double bond and then consider other types of compound which also exhibit geometrical isomerism. A carbon-carbon double bond consists of a sigma bond and a pi bond, while the sigma bond is formed by the overlapping of sp2 hybrid orbitals of two carbon atoms along the internuclear axes. Pi bond is formed by the sideways overlapping of the hybridized p orbitals of the two carbon atoms above and below the plane of atoms. Because of this type of overlapping rotation around the carbon double bond is strongly hindered and can take place only if the pi bond breaks. But this would require about 284 kg of energy per mole, which is not available to the molecules at room temperature. Due to this hindered rotation around the carbon-carbon double bond, the relative positions of groups attached to doubly bond carbon atoms get fixed. As a result, several higher alkenes and other substituted products can exist in two distinct isomeric forms which differ from each other in the relative distribution of groups in space around the double bond. For example, malic acid and fumaric acid afford a very well known example of compounds which exist in the geometrically isomeric forms as shown below. These two isomers are like one another with respect to which atoms are attached to which other atoms but differ from each other in the relative arrangement of atom in space. In malic acid, the two carboxylic groups on the same side of the molecule, while in the fumaric acid the two carboxylic like on opposite sides. Such isomers which have the same structural formulae but differ in the relative spatial arrangement of atoms about the double bond are called geometrical isomers, and the phenomena is known as geometrical isomerism. Condition for geometrical isomerism: there are two necessary conditions for a compound to exhibit geometrical isomerism. These are: first, the molecule must contain a carbon-carbon double bond, the rotation around which is strongly hindered. Second is each of the two doubly bond atoms should have two unlike groups attached to it, as for instance ABC equal to CAB. The formula ABC equal to CAB can have two arrangements in space which represent the geometrical isomers as shown below. For example, two butene exist in the form of geometrical isomers as depicted below. Sometimes the two groups attached to one doubly bond carbon may be together different than those attached to other carbon atoms such as ABC equal to CCD. Even then, geometrical isomerism would be exhibited. However, this is not an essential condition. Nomenclature of geometrical isomers, cis and trans system. This method originally used for denoting the configurations of geometrical isomers is known as cis-trans system. In this system, the names of the geometrical isomers having different configuration are distinguished by using the prefix cis or trans before the name of the compound. The prefix cis is used when similar groups are on the same side of the molecule, while the prefix trans is used when similar groups are on opposite sides as illustrated below. Limitations of cis and trans system of nomenclature. The cis and trans system of nomenclature of geometrical isomers is not universally applicable. It cannot be employed in case of compounds where all the four substituents attached to the two doubly bond carbon atoms are different from each other. For example, let us consider the following compounds. Here we can see that I and Cl are cis to each other, but we can also equally well say that Br and Cl are trans to each other. Therefore, it becomes difficult to name such a substance either as cis or trans isomer. E and Z system of nomenclature. In a view of the limitation of the cis-trans system, a more general system of a nomenclature of geometrical isomers known as E and Z system is now being adopted. E Z system is based on the sequence rules originally developed by Chan, Prelog, and Ingold for R and S systems of specifying configuration of optical isomers. For specifying the configuration of geometrical isomers as E or Z, the following rules are followed. First, the two atoms or groups attached to each carbon of the double bond are assigned a higher or lower priority according to the priority sequence rules R and S system of the optical isomers. Second is the if the higher priority atoms or groups on each carbon of the double bond are the same side, the atoms or groups of higher priority are on opposite side, the configuration is termed as E. Thus we know that atoms having higher atomic number have higher priority. Therefore, out of C and Cl attached to one Cl has higher priority. In the same way, out of Br and I attached to 2C, I has higher priority. Some more examples of assigning E and Z designation are given below. It may be noted that most of the compounds that we would normally designate cis are designate Z. Similarly, most of the compounds that we would designate trans are designed E. Nomenclature of compounds containing more than one double bond. If a compound contains two or double bonds around which geometrical isomerism is possible, E and Z designation are given to each double bond. For example, 2Z 4Z 2 4 hexadiene, 2E 4Z 2 hexadiene, 2Z 4E 2 4 hexadiene, 2E 4E 2 4 hexadiene. For the compounds which exhibit geometrical isomerism, draw the structure for the isomerism and names them. Determination of configuration of geometrical isomers. The following methods can be employed for determining the configuration of geometrical isomers. For dipole moment. Determination of the dipole moment of a pair of geometrical isomers can be quite helpful. Can designate a particular isomer as a cis or trans. For instance, in a case of compounds of the type ABC equal to CAB, the net double dipole moment of a trans isomer is expected to be zero. This is because the similar groups are on opposite sides of the molecule and therefore the bond polarities cancel out each other. In contrast, the double bond polarities are not cancelled in case of cis isomer and therefore it has a definite dipole moment. Thus, cis-2-butene should have a small dipole moment while the dipole moment of trans-2-butene should be zero. The following experimental data goes to support the above predictions. Second is from boiling points. In general, cis isomers have higher boiling points than trans isomers. This is evidently because of the higher polarities and higher dipole moments of cis isomers, which leads to greater intermolecular attraction. For example, the boiling point of cis tubutene is 277 Kelvin while that of trans isomer is 274 Kelvin. 4. From melting points. Generally speaking, trans isomers have higher melting points than cis compounds. This is because trans isomers are more symmetrical and can be more closely packed in the crystal lattice. For example, malic acid has melting point 403 Kelvin and fumaric acid has melting point 575 Kelvin. From the formation of ring compounds. Sometimes it is possible to distinguish between two geometric isomers by chemical reactions which lead to the formation of rings. Cis isomer is likely to undergo ring closure much more readily than trans isomer. For example, malic acid loses water when heated to 423 Kelvin to form malic anhydride. On other hand, fumaric acid does not give an anhydride at this room temperature. By conversion into compounds of known configuration, sometimes a particular geometrical isomer can be converted into a compound of known configuration without any change in configuration around double bond. From the configuration of the product formed by the configuration of the starting compound can be deduced. For example, one of the geometrical isomers of trichloro crotonic acid on hydrolysis yields fumaric acid while the other isomer does not. Since fumaric acid has a trans configuration, the isomer of trichlorocrotonic acid which changes into fumaric acid must also be the transform that is given below. Sixth is from the formation of type of optical isomer. In certain reactions, geometrical isomers having carbon-carbon double bond change into products having newly created stereogenic centers. From the type of optical isomers formed, the cis or trans nature of the starting compounds can be determined. For example, malic acid on hydrogylation with KMnO4 gives mesotartaric acid, while fumaric acid forms racemic mixture of tartaric acid as shown below. Geometrical isomerism in compounds other than alkenes. Geometrical isomerism can also be exhibited than the presence of carbon-carbon double bond. Thus, geometrical isomerism is also shown by the compounds having carbon nitrogen double bonds, nitrogen nitrogen double bonds, and even some cyclic compounds which do not contain any double bond as discussed below. First is geometrical isomerism in oximes. Oximes are the compounds formed by the reaction between aldehyde or ketones and hydroxylamine, that is phi. When aldehyde or ketone plus H2NOH reacts, C double bond ONOH is formed. Or when acetaldehyde plus H2NOH reacts, acetyl dioxime is produced. Oximes exhibit geometrical isomerism due to hindered rotation around carbon nitrogen double bond, while the doubly bound nitrogen carry only OH group attached to it. The doubly bound carbon must have two unlike groups attached to it for geometrical isomerism to be possible. For example, geometrical isomers of acetyl-dioxamide. The configurations of geometrical isomers of oximes are usually denoted by prefixes sin and anti instead of cis and trans respectively. In case of aldoxymes, the isomer is named as sine if OH group attached to nitrogen is on the same side as attached to carbon. If the OH group attached to nitrogen is on the opposite side to hydrogen, the isomer is called anti. In case of ketoxymes, the isomer is named as sine of if the OH group attached to nitrogen is on the same side as the group attached to carbon, which comes first in the name of the compounds. If they are on opposite sides, the name is anti. Determination of configuration of oximes. The actual configuration of geometrical isomers of aldoxymes is determined by their relative assay of dehydration when treated with a dehydrating agent such as acetic anhydride. And anti-aldoxymes undergo dehydration easily to form nitriles. For examples, when anti-aldoxime reacts in the presence of ACT2O, nitrile is formed and H2O is a side product. On the other hand, when a cyanitrile is treated with acetic anhydride followed by aqueous solution of sodium carbonate, original oxime is regenerated. The configuration of ketoxymes are determined on the basis of Beckmann reagent. When treated with an acidic reagent such PCl5, P2O5 and COCl2, the oxime undergoes reagent to form a substituted amide. The structure of the amide thus formed helps to establish the configuration of the oxime. However, the detailed procedure would be discussed later. Second is geometrical isomerism in alicyclic compounds. There are many substituted alicyclic compounds which show geometrical isomerism. This is because the presence of a ring can also prevent rotation around carbon-carbon single bond. Therefore, geometrical isomers because become possible if there are two carbons on a ring, each of which is attached to two unlike groups. These two carbons may or may not be adjacent to each other. For example, dimethyl cyclopropane exists in two geometric forms, one in which the two methyl groups are on the same side of the ring and the other in which they are on opposite side of the ring as shown below. Similarly, cyclobutane 1,3-dicarboxylic acid and cyclopentane 1,2-diol also exhibit geometrical isomerism. Conformations. Due to the axial symmetry, the single bond allows freedom of rotation about it. As a result of this, the molecules of a compound can have different relative arrangement of their atoms in space, which can be converted one into the other by rotation around the single bond. Such arrangement in space of the atoms in a molecule that can be readily interconverted by rotation around single bonds are called conformation or conformers. The existence of different conformations of a compound constitute a special type of stereoisomerism. We will discuss some aspect of the phenomena with reference to alkanes and cycloalkanes. Figure 2.12 represents symmetrical electron distribution representing a single bond between sp3 hybrid orbital of two carbon atoms. Conformation of ethane. Ethane is the simplest molecule for which the infinite number of conformations are possible. The central bond in the molecule of ethane is a single bond between two carbon atoms, each of which is further linked to three hydrogen atoms. If one of the carbon atoms of ethane is allowed to rotate around the central bond while the other is held still, a very large number of arrangements of the hydrogens of the one carbon with respect to the hydrogens of the other carbon can be obtained. The basic structure of the molecule and various bond lengths and bond angles, however, remain the same in all the arrangements or conformations. Of the infinite number of possible conformations of ethane, two conformations represent the extremes. They are called eclipsed conformation and staggered conformation. In the eclipsed conformation, the hydrogen of one carbon are directly behind those of the other. In the staggered conformation, the hydrogen of two carbon atoms are staggered with respect to one another. Representation of conformations. Since it is not very convenient to represent three-dimensional formula on paper, certain conventions have been adopted for projecting the conformation on paper. The two commonly used methods are as follows. First, Sahor's formula. In this representation, the molecules is viewed slightly from above and from the right and then projected on the paper. The bond between the two carbon atoms is drawn diagonally and the of a relatively greater length for the sake of clarity. The lower left hand carbon is taken as front carbon and the upper right hand carbon as the back carbon. The three atoms or group attached to each carbon are shown tetrahedrally in space. The Sahor's representation of eclipsed and staggered configuration of ethane are shown in figure 2.13. Figure 2.13 represents the Sahor's representation of eclipsed staggered configuration of ethane. Figure 1 represents the eclipse structure and figure 2 represents the staggered configurations. Second is Newman projection formula. Newman devised a very simple method of projecting three-dimensional formula on paper which are known as Newman projection. In this formula, the molecule is viewed from the front. The carbon atom nearer to the eye is represented by a point or dot and the three atoms or group are shown attached to it by three lines at angle of 120 degree to each other. The carbon atom farther from the eye is represented by a circle and the three atoms or groups are shown attached to it by shorter lines ending at the circumference of the circle at the angle 120 degree to each other. Newman projection for eclipsed and staggered conformations of ethane are shown below in figure 2.14. Figure 2.14 represents Newman projection for the conformation of ethane. First is eclipsed and second is staggered. Difference between conformation and configuration. Conformation, as stated above, conformation are three-dimensional arrangement in space of the atoms in a molecule that can be interconverted merely by rotation around single bonds. For example, figure displays two such arrangements known as eclipsed and staggered configurations of ethane which are readily interconvertible by rotation around the carbon-carbon single bond configurations. As already stated, configuration are three-dimensional arrangements in space of the atoms in a molecule that cannot be interconverted merely by rotation about a bond. For example, the configuration of minus lactic acid and plus lactic acid, which are not interconvertible by rotation about a bond, are shown in figure 2.15. Figure 2.15 represent configuration of minus and plus lactic acid. Figure 1 represent lactic acid and figure 2 represent plus lactic acid. In the light of above definition, the main points of difference between conformation and configuration may be summed up as follows. The difference in the conformation and configuration as follow. First difference is that these are three-dimensional arrangements in space of the atoms in a molecule which are interconvertible by rotation around a single bond. But in configurations, these are three-dimensional arrangements in space of the atoms in a molecule which are not interconvertible by rotation around a bond. In conformation, their interconversion does not require any breaking and making of bonds. But in configurations, their interconversion is possible only through breaking and making of bonds. In conformations, their existence leads to the phenomena of conformational isomerism. In configurations, their existence is involved by the phenomena of geometrical and optical isomers, which are also collectively known as configuration isomerism. In conformation, since conformations are readily interconvertible, they cannot be isolated from each other. As such, conformational isomerism exists only as a mixture of different configuration. Since configuration are not easily convertible, they can be isolated from each other and stored as pure substances. As such, configurational isomer can exist as pure individual substances. Conformational analysis of ethane. It has been stated that earlier that a single bond allows freedom of rotation around it. However, it must be pointed out that rotation around the single bond is not completely free. If it were so, the potential energy of differential conformation of a compound should have been the same. But in actual practice, the potential energy of molecules changes somewhat with rotation around the C-C single bond. The study of energy changes which occur in a molecule due to rotation around carbon-carbon single bonds is known as conformational analysis. Let us first study the energy changes taking place in ethane. The potential energy of an ethane molecule is minimum for the staggered conformation, increases with rotation and becomes maximum for the eclipsed conformation. The difference between the two extreme conformation being 12.55 kg per mole. This difference in energy constituent an energy barrier to rotation around the single bond. The energy barrier to rotation in ethane is said to be due to toroidal strain, and the energy required to rotate the ethane molecule about the carbon-carbon bond is toroidal energy. These terms are explained a little later in Sec 2.24. Figure 2.16 determines that changes in potential energy during rotation about carbon-carbon single bond of ethane. The energy barrier of rotation described above is, however, not large enough to prevent rotation altogether even at ordinary temperature. The molecules possess sufficient thermal or kinetic energy to overcome the energy barrier through effective collisions, and thus the conformation keeping on changing from one to another. In the other words, rotation around the single bond can still take place nearly freely, being only slightly restricted by the energy barrier. As such, it is not possible to separate different conformation of ethane. It is quite obvious, however, that at any moment most of the ethane molecules would exist in the staggered conformation due to its minimum energy and therefore maximum stability. In other words, any molecule spends most of times in the staggered conformation, which is the most stable conformation. Conformational analysis of propane. If one of the hydrogens of ethane is replaced by another atom or group, the situation remains practically unchanged. For example, let us consider the case of propane in which one of the hydrogen atoms of ethane has been replaced by methyl group, that is, in propane, rotation can take place about either of the two carbon-carbon bonds, even though the methyl group is considerably larger than hydrogen. The energy difference between the two extreme conformation, eclipsed and staggered, is 13.8 kg per mole, which is nearly the same as in case of ethane. The most stable and preferred conformation is of course the staggered conformation, although it can almost freely change into the eclipsed conformation and vice versa. In figure 2.17, Newman's projection for the conformation of propane. First is eclipsed and second is staggered. Conformational analysis of N-butane. The molecule of N-butane, which may be considered as distributed ethane, is somewhat more complex for conformational studies. If we consider the rotation only around the single bond between the two inner carbon atoms of N-butane, if we have a molecule similar to ethane but with a bulky group in place of hydrogen atom of each carbon, in contrast with ethane and butane can have several different staggered and eclipsed conformations due to this presence of methyl groups. Four of the important conformations are anti-eclipsed, gauge and fully eclipsed. They are shown in figure 2.18. The anti-conformation is an extreme staggered conformation in which the methyl groups are as far apart as possible if the angle of rotation around the C2 and C3 single bond is assumed to be 0 for this conformation, and one of the C2 or C3 carbon atoms is rotated through an angle of 60 degree. An eclipsed conformation results in the conformation the methyl group attached to one carbon is not at the back of the methyl group attached to other carbon but is at the back of hydrogen attached to the carbon. Rotation by another 60 degree leads to another staggered conformation called gauge conformation, in which the two methyl groups are only 60 degree apart. Further rotation by 60 degree gives rise to the fully eclipsed conformation, in which the two methyl groups are at the back of each one further successive relations by 60 degree. We pass through another gauge conformation and another eclipsed conformation and finally arrive at the anti-conformation again and completion of 360 degree. The difference in energy contents between conformations first and fourth is about 18.4 kg per mole, between first and second or sixth about 14.6 kg per mole, in between first and third or fifth only about 3.8 kg per mole as shown in figure 2.19. Therefore, the order of stabilities of different conformation of N-butane is NT is more stable than gauge, gauge is more stable than eclipsed, eclipsed is more stable than fully eclipsed. It is a apartment that due to very small difference in their energies, anti-conformation is only slightly more stable than gauge conformation. The difference in the energy of anti and gauge forms is due to steric strain, which is discussed in Sec 3.24. It can be easily seen that the rotation about the carbon-carbon single bond in N-butane is again nearly free and the different conformation cannot be isolated at any time. N-butane consists mainly of an equilibrium mixture of anti and gauge conformation, with the anti conformation having the highest percentage, about 67% at 295 Kelvin. It will be interesting to compare the spatial arrangement of two gauge conformation of N-butane. It may be easily seen that these two conform are also mirror images and hence enantiomers of each other. Such conformational isomers, which are also mirror images of each other, are known as conformational enantiomers. However, unlike conformational enantiomers, conformational isomers are readily interconvertible by rotation around a bond. If we compare the anti-conformation of N-butane with its gauge conforms, it is found that first and third are not mirror images of each other. Such pairs of conforms are termed as conformational diastereomers. Thus, we find that conformational isomers can also exist as pair of enantiomers or diastereomers, which however are readily inconvertible. Conformation of cyclohexane. We have so far studied the conformation of open chain compounds. Let us now have a look at the conformation of cycloalkanes by considering the case of cyclohexane. Cyclohexane is a multiplanar or a puckered ring compound in which carbon atom are sp3 hybridized state and all the bond angles are equal to normal tetrahedral angle. Of the various possible conformations of cyclohexane, the two most important conformations are: first is chair conformation and second is boat conformation. First is chair conformation. This is the most stable and therefore the most preferred conformation of cyclohexane. In this conformation, all the bond angles are tetrahedral and all the CH bonds on adjacent carbon atoms are staggered position. In figure 2.21, at the same time, there is no steric interference or dipole-dipole interaction between the non-bonded atoms. Thus, the conformation is essentially free of strain and has a minimum energy. In other words, this is the most stable conformation of cyclohexane. Second is boat form conformation. This is the second most important conformation of cyclohexane and is depicted in figure 2.22. As in the chair conformation, there is no angle strain in the boat conformation since all the bond angles in it are tetrahedral, but in boat conformation the hydrogens on 4 of carbons are eclipsed. As a result, there is a considerable toroidal strain. Figure 2.22 represents the boat conformation of cyclohexane. At the same time, the two hydrogens pointing towards each other at C1 and C4 are very close together. The distance between them being only 183 picometer or 1.83 angstrom, while the sum of them their van der Waals radii is 250 picometer or 2.5 angstrom. This gives rise to van der Waals strain also in the molecule. Due to toroidal and van der Waals strain in it, the boat conformation is naturally much less stable by 28.8 kg per mole than the chair conformation. As such, only very few molecules of cyclohexane exist in boat conformation. Other conformation, in addition to the chair and boat forms of cyclohexane, several other conformations are also possible as discussed below. Twist boat or skew boat conformation. Let us consider a model of the boat conformation of cyclohexane as shown in figure 2.23a. Suppose we hold C2 and C3 in one hand and C4 and C5 in other hand, and the twist the molecule so that C3 and 6 go down while C2 and C5 comes up. It will be noticed that during this twisting, the flagpole hydrogens on C1 and C4 move apart and at the same time two hydrogens on C3 and C6 begin to move close together. In this way, we get another conformation called twist boat or skew boat conformation, in which the distance between HA and HB is equal to between HC and HD. It is quite evident that in the conformation, the van der Waals strain between flagpole hydrogens is minimum. At the same time, the toroidal strain on C2 and C3 and C2 and C6 is also appreciably reduced. As such, the twist boat conformation is more stable than the boat conformation by about 6.7 kg per mole, although it is still less stable than chair conformation by 23 kg per mole. Figure 2.23 represents the twisting of boat conformation. Half chair conformation. In between the chair conformation, twist boat conformation lies yet another conformation known as half chair conformation in figure 2.24. It has both angle and toroidal strains and has about 46 kg per mole higher energy than chair form. In fact, it represents merely a transition state conformation. Next is energy relationship between different conformations. The energy relationship between the different conformation of cyclohexane as shown in figure 2.25. It must be pointed out that the energy difference between any two conformations is too small to permit their isolation. It is evident that the order of relative stabilities of different conformation of cyclohexane is chair conformation is more stable than twist boat conformation. Twist boat conformation is more stable than boat conformation, and boat conformation is more stable than half chair conformation. Equatorial and axial bonds in cyclohexane. Since the chair conformation is the most preferred and the most important conformation of cyclohexane, let us examine its little more closely. Although the cyclohexane ring is not flat, if can imagine an average or general plane of the ring, now we consider the position of various hydrogen atoms in the chair conformation. We find that there are two different kinds of hydrogen. Six of the hydrogens point sideways along the general plane of the ring are called equatorial hydrogens because they are situated along the general plane of equatorial belt of the molecule. The other six hydrogen in two groups of three each lie above or below the general plane and point along an axis perpendicular to the ring. These are known as axial hydrogens. The bonds by which an equatorial hydrogen is held is called an equatorial bond, and the bond by which an axial hydrogen is held is called axial bond. There is one equatorial and one axial bond on which each carbon in the chair configuration of cyclohexane. Figure 2.26 represents the equatorial and axial bonds in cyclohexane. It may be pointed out that the distance between hydrogen on adjacent carbon atoms in cyclohexane is 230 picometer or 2.3 angstrom, which is the same as in staggered ethane. However, axial hydrogens on the same side of the molecule are situated rather close together, even though they are linked to alternate carbon atoms. But it may be noted that distance between such hydrogens is also 230 picometer or 2.3 angstrom. It is interesting to note that the axial and equatorial hydrogens in cyclohexane can interchange their position. This is because their change conformation of cyclohexane is flexible and one chair conformation can change into another chair conformation by process known as ring inversion ring flipping. As this happens, all hydrogen originally axial become equatorial and vice versa, but one chair conformation is perfectly equivalent to other and they cannot be distinguished from each other. Conversion of Fisher projection formulae into Sahor's formulae and Newman's projection formulae. In conclusion of the discussion on the stereochemistry of organic compounds, we may point out an interesting drawback of Fisher projection formulae of diastereomers having two chiral carbon atoms. The Fisher projection formulae of such compounds correspond to the less stable eclipsed conformation involving maximum crowding between the substituent group attached to the two chiral carbon atoms. But actually the molecules acquire the shape which correspond to the staggered form in which the substituents are so far apart from each other as possible. Therefore, the best way of representing such molecule is to depict them in their staggered form by means of Sahor's formulae or Newman's projection formulae as explained below. Conversion of Fisher projection formulae into Sahor's formula. This involves two steps as given below. First step is write the Fisher projection formula and change it into the equivalent eclipsed representation in terms of Sahor's formula. Second is rotate one of the chiral carbon atom by angle of 180 degree around the bond between the two chiral carbon to get the Sahor's representation of the staggered form. For example, let us convert 2s3 or 3-bromobutane 2-ol from Fisher projection formula to Sahor's formula. Conversion of Fisher projection formula into Newman's projection formula. This also involves a similar procedure in which the Fisher projection formula is first translated into the equivalent eclipsed form in terms of Newman's projection formula. The latter is then changed into the staggered form by rotating through the angle of 180 degree around the bond between the two chiral carbons. For example, 2s3r 3-bromobutane 2-ol is converted into Newman projection.